Now this guy right here, we've talked about this before. This is the population proportion. This is the parameter, proportion. And unfortunately, remember how I always said, well, lowercase Greek letters imply parameters. Well, you're stuck with P. Sorry, my bad. All right, so that said, here's the problem. We took one sample of 5,000. We were told that 4,000 of the people had a household that had a dog in it. That's one of these guys, okay? Now, with this confidence interval, the biggest error, let's talk about the error. No, let's talk about the correct way to say this first. The correct way to say a 95% confidence interval is this. If we replicated this study over and over and over again, and then we created confidence intervals over and over and over again, what would happen is some of those confidence intervals, let's bounce over here, what I would get is a bunch of confidence intervals, right? So this would be the confidence interval that was created from P1, all right? And I'll just do this a couple times because I know you guys are going to shoot me if I don't. P1 minus E minus some error, and then P2 hat plus some error, whoops. And then if I do this, P2 hat, then that's going to turn into P2 hat minus some error, that's a 2, and then P2, it should be a 1. Sorry about that, you guys. P2 hat plus some error, etc., etc. So what I'm going to end up with is a whole bunch of these confidence intervals. All right? A ton of them, because think, sampling distribution. I mean, there's a lot of ways to make samples of size n equals 5,000, with or without replication, with or without replacement. Okay? What's going to happen is 95%, if I do this a whole bunch of times because of the law of large numbers, 95% of these confidence intervals will actually contain the proportion. So let's write that out. So 95% of the CIs made by reproducing the study, or the samples, think about it that way. Study, why am I writing? Don't mind me. Sample. Many times will contain the actual population proportion, which is P. All right? If I do it a whole bunch of times, then 95% of those will contain the true population proportion. All right, now, the most common error, and I'll do this in red, the error is to say this, 95% confidence interval. Now remember, this is an error, so those of you that have walked away from your computers and let it run and come back, this is the error. This is wrong. All right? The wrong way to think of a confidence interval is that the probability that a single CI, which is written as P hat minus E, P hat plus E, that it contains P, the actual parameter, remember P is the actual population proportion, is 0.95. This is dead wrong. All right? What you really need to think about with this is if this P hat is a point estimate, then really this interval is a point interval. It's an interval that's created by a point estimate. Okay? Now, we are hoping, we are crossing our fingers that the true population proportion lives in this confidence interval, but we don't know. We would only know if we did it a whole bunch of times. If we took n equals 5,000 samples of that size and did that over and over and over and over again, and we would still only be 95% sure. We'd only be 95% confident. In other words, out of 100 of those, we could, well, let's think out of 100,000 of those, because that's a whole boatload, right? If I built 100,000 of these confidence intervals right here, I'm still only 95% confident. In other words, I can guess that 95,000 out of that 100,000 are going to actually contain the population proportion. Now you may say, well, Ripley, why? I don't understand. Why are we building these things in the first place? Well, because we don't know what this guy is, and we're trying to figure it out. Like where you're going to see this in the presidential campaign is what percentage of Americans support the president? What percentage of Americans support the candidate? All right, you can't, unless you roll around at how many people are there in America, 350 million, something like that, 300 million, whatever. Unless you walk around to every single person and poll them, which clearly isn't feasible, it isn't practical, it isn't economical, it ain't gonna happen, right? What you need is you need to take a point estimate, and then you need to build a confidence interval around it, and you say, okay, somewhere between, well, I don't know what the president's approval ratings are right now. I think they're hovering around 40%, right? But what does that mean, right? That just came out of a point estimate. So we could say, okay, somewhere between 0.32 and 0.48, or 32 to 48% of Americans approve of the president's work on some issue. Now look at that. That is a huge interval. It's very, very big. All right, and we're not even sure that the actual parameter lives there. However, if we do this, if let's say that for this guy we just polled 12,000 people. All right, just called them up, polled them. Now, I understand that there are confounding variables with that as well, right? If you don't have a phone, if you have a cell phone that can't be reached, et cetera, we know about that problem, right? People that answer their phone tend to be elderly. They have different opinions of the president. Hopefully your brain is starting to crank through this and be like, something's fishy with this whole statistics thing. There are lies, there are damn lies, and there are statistics. All right, now, I'm sorry, I digress. Allow me to hop off my soapbox here for just a sec. We are not even sure that this confidence interval even contains the parameter. We're just hoping. And if we did this a whole bunch of times, we did it a ton of times, then we could say that we are 95% confident. I've seen confidence intervals that are as low, as weak as 90%. I've seen them as high as 99%, but 95% seems to be the union standard. That's the one that you're pretty much going to go for every single time. Okay? All right. Now, again, all I just gave you was the theoretical foundation for confidence intervals. We'll play. There are some applets that we're going to play with in class, and I'll show you how all this works out. So I hope you're ready to do a little bit of mathematics. All right. Now, even though I just said that we're going to take these point estimates and it requires us to do a whole bunch of replication to be truly confident, it's going to feel like I'm going to go back on that for just a little bit. But the idea behind this is truly that we know that proportions, that sample proportions are unbiased estimators, okay? So they have a tendency to head towards the mean. Not only do we, or the mean, the actual population proportion. Not only that, but we know that the sampling distributions for population proportions distribute themselves on a normal curve, right? With the true P here, okay? Now, this gets a little tricky to wrap your brain around, all right? But we'll do our best. What's going to happen is this P is unknown. Let's make sure we understand that. And we're really kind of taking a leap of faith here. What we're saying is, instead of, we don't know what the true population proportion is. It's too difficult to figure out. You would have to take a census, and even those are flawed. So what we're saying is, we're going to build, this is where it gets really cool. We're going to build a confidence interval around P hat, our point estimate, okay? And we get to do that because it's an unbiased estimator. But we're really going to say, okay, let's assume that P hat is really, really close to the population proportion. And then what we're going to do is we're going to build out our confidence interval on this normal curve. And remember back in the day when I think we did it for women's heights, where we wanted to find the middle 80% of all women's heights. We're going to do exactly the same thing, only we're going to do it with 90. Remember, if we talk about, let's just keep it simple. If we talk about a 95% confidence interval, really the mathematical foundation for building a 95% confidence interval is taking p hat, sticking it in the middle of this normal curve right here, and then grabbing 95% of the data in the middle. That's really it. That's the mathematical foundation. We're saying, okay, we know that the p hat is flawed. However, let's assume that it's pretty darn close. And if we can build a confidence interval on either side, so think of this distance right here as minus error, right? And think of this distance here as plus error, then what we end up with is we end up with 95% in the middle, and think about that. Remember the symmetric property of the normal curve. The errors outside here, which truly are the errors, right? They're outside of the 95% confidence interval. Then this would be 0.025, and this would be 0.025, or 2.5%, 2.5%, and 2.5%, right? Because the total has to add up to 100%. Does that make sense? Think about that for just a sec. Again, we're just using a point estimate, which I realize is flawed, but we have some mathematical and some statistical facts that can back us up. Okay? So, remember what we called, I want you guys to think about this again. I'm going to go back to my black pen. Remember what this boundary line was called once we're on the normal curve. What was the boundary line called for which the area above was 0.025? Do you remember what that was called? It's called Z alpha, right? Now, for confidence intervals, we're going to tweak this just a little bit. What we're really saying is we're going to say that this is Z alpha over 2 because this area plus this area is really the error of our, it's not the error, I don't want to say that too many times. It's outside of our interval. It's the missing part of our interval, which is we're going to say alpha equals 0.05 or 5%. So really each one of these guys, if alpha is 0.05, then this is going to be alpha over 2. Alpha halves is equal to 0.025 or 2.5%. Okay? Now remember, back a couple chapters ago, the z-score that corresponded to having a certain fixed area above it was referred to as z sub alpha. But we're stealing alpha kind of twice here. Just it happens. I apologize for that.